Hi, so this is going to be the notes for section 2.5, which is called the chain rule. This is another way to take derivatives. I guess I shouldn't say another way, but it's a way to take derivatives depending on what kind of function you need to take a derivative of. So far we haven't had this rule yet, so certain derivatives we couldn't take, but now we'll be able to. So here are the guided notes. As you know, you just need to follow along and fill them out. And just make sure that you are paying attention. There is a small quiz just to make sure that you were. There we go. Okay, so notice that we have this idea y of u equals u squared, and u of x equals x squared plus 3x. And then the question is, what is dy dx? So when we ask a question like that, it's really just asking you to use the idea of composition. So y of x is really just taking, y of u of x, like that. And when we do that, that's going to be, here is your y of u, and then I'm going to put u of x inside. So this function will not look surprising in any way, but the idea there is it's the composition of two functions. And what you really want to see is that in situations like this, which is how we'll be able to take these derivatives, you want to, here we go, let me just, maybe I can probably figure out a way to do that faster. Here's an inner function, and here's the idea of the outer function. So that's why we reviewed composition a while back. So taking a derivative like this, you might say, well, I could do that. I could multiply x squared plus 3x times itself, and I could take the derivative of each piece. I learned that previously, and you'd be right. But what if instead of x squared plus 3x squared, this was a lot bigger? So what I'm saying here is, we know that just from algebra, that this is x to the fourth plus 6x cubed plus 9x squared. So again, we could multiply it out if you wanted to. And then to take the derivative of this, I'm using this notation here. I'm just taking the derivative of this thing y with respect to x, and that's going to give me 4x cubed plus 18x squared plus 18x. So that's our derivative, okay, and that is what it is. But what I was saying earlier is, what if instead of the squared you had x squared plus 3x, and then up here you had some really big exponent? So in my notes I have something like this. Okay, so what if you had this to the 200? So of course you're never going to multiply that out 200 times and then take the derivative. It would just be too much, and you don't have to. So we have what's called the chain rule, and it basically says that if you have two functions that are both differentiable, and remember that being differentiable implies what? That you have continuity as well, and you can look at those two functions as a composition like we have here, then you can take the derivative of the composition. And we won't look at them as necessarily separate functions, more kind of an outer and inner idea, but this is the true definition here. It says you take the derivative of the outer function and you keep the inner function inside of it, and you multiply that by the derivative of the inner function. So that's what I have here in this note. So you want to differentiate the outer function, okay, and that's just at g of x, just that stays the same, then multiply by the derivative of whatever that inner function is. That's the idea. And of course we're going to practice this now. So let's take a look at a few examples. So here is the y, this is going to be, I'm going to do this first, this second, and this is at the bottom of your page, but I moved it up so that there would be enough space. So the first thing we'll do is find y prime if y equals, and then in parentheses x squared plus 3x squared. So I already did this earlier, not that long ago, but now what I'm going to do is do it again, but I'm going to show you how to do it using the chain rule. So in order to find the derivative, following what we had on the last slide, and I may go back there, the idea here is our outer function is just this idea of something squared. And we know that the derivative of this idea of being squared is that we bring down the 2 and then we subtract 1 from the exponent, like thinking about the power rule. So the only difference is we still have that. It's just that with the chain rule, what the chain rule says, and of course this is true, this is not just, you know, this has been proved. If I change here to say a dark red, I'm going to keep this inside the same. So it's still going to be x squared plus 3x. And let me come back just to remind you down here that I'm taking the derivative of the outer part. That is the 2 and the 1. Then the inside stays the same. So that's my g of x. My inner function stays the same. And then I multiply that by the derivative of that inner function. So now I'm just thinking about multiplying times the derivative of the x squared plus 3x. And that's just using, you know, our general power rules and other differentiation rules that we've already learned. So 2x plus 3. Okay. And so that's our derivative. I want to show you that that's the same as what I did earlier today. So take a moment and just multiply that out. You can pause the video and multiply it out. And then when you start it again, I'll do the answer here. So pause, multiply it out, and then check. Okay, so this is 2x squared plus 6x times 2x plus 3. And we're just going to multiply this out. And I'll show you, this is not something we always have to do. Again, I'm really just trying to show you that this does work here. That either way is going to get you the right answer. But we notice that just by multiplying out and simplifying, we will have the same thing that we had when I multiplied it out originally and then took the derivative. Now I took the derivative and multiplied it out using two different methods. So answer is the same as what we had over here on the last page. Okay, but yeah, the big idea here is, what if we have, instead of 2, we have 200? This is where the chain rule becomes imperative. If you don't have the chain rule, like, there'd be literally no way to do this. So, using the chain rule. It's early, I got on my slippers, got my coffee, trying to make this happen, man. Remote instruction, here we go. So, what the chain rule tells us is we're still thinking about this idea of taking the derivative of something to the 200, and following that generalized power rule that tells us to bring down the 200 and then take 1 away from the exponent, 199. And of course, I'm not going to multiply this out when it's over. And then, just like we had before, I mean, there's nothing else that's different from what we had before. We keep the inside the same. Let me change the ink color here. So we keep the inside the same, x squared plus 3x. And then we don't want to forget that we have to multiply, and this is according to the definition of the chain rule, 2x plus 3. And again, not multiplying this out. This is the chain rule. This is the derivative, so I am done with this. Okay. Coming up here to number 3, let's notice that it's just using, you know, slightly different notation. It's just to get you to think about the idea of composition, so hopefully it's not too overwhelming for you. But the idea would be to first create y of x, because you have basically here y of u of x. So let's just do the composition. We're going to have secant, and what's going to be inside the secant. So think about that. I am sure that there is a way to change this pen color where I don't need to sit here and think around, but I will learn that for the next one. Growth mindset. Okay, so I'm going to put in my x cubed plus 3x. So this is just creating and showing you the composition. Generally, you will not have to do that. I've mentioned that already. This is just the idea of, getting it done. So if you want, you could definitely pause this and take a moment and try to do it, and then come back and see what the answer is. So I'm going to take my derivative. I guess technically I need to use this notation since that's what they asked. It is the same, but let's try to be consistent. I don't know why I said they asked. I am the person that's made these notes, so I guess I am the person that asked. So anyway, coming back here. No. All right. So taking the derivative of something like this, and this is true for any of the trig functions that we're going to be taking care of here, is you want to remember that you're first thinking of your outer function, which in this case is secant. We know that the derivative of secant is secant something times tan of something. Now when that thing is just x, you have secant x tan x. But when you don't, like we don't in this case, here we have x cubed plus 3x inside. The issue with that is, well, can't do the same thing. So I'm going to change it to x cubed plus 3x because that's actually what I had inside, so that's going to stay the same. So remembering that your chain rule, the inner function stays the same when you take the derivative of the outer function. But then another important part of the chain rule is multiplying by the derivative of that inner piece, and that is a common mistake that students forget. Or they'll take the derivative and stick it inside the secant and the tan, like in something like this. So derivative of x cubed plus 3x, write that out. There we go. And we are fine with that. There is really nothing else we can do. There'd be no reason to do any more simplification or anything, so I would just leave it. You are done with that problem. Remember that if you have any questions on any of this, save that, write them down, and then save those for the discussion part that we have coming up in, a little bit after you do the video quiz, and then you can ask questions in the discussion. All right. So a few more problems here. I mean, quite a bit more, but just practicing more of the the chain rule, and figuring out when you need it. So looking at the problem at the top, don't forget that with any trig functions, what you see here is the same as saying what you see here. Okay, so those two things are equivalent. So when we put the cube inside the tangent like that, in that way, that's the same as saying tan x quantity cubed. And that's why the chain rule is needed. So in this case, your outer function is in fact, that is my laundry, if you can hear that bell. The outer function here is that idea of the cubed. So we're going to bring the 3 down, and that's going to be squared. So that's just using that power rule. That's no different. And that's actually what I'm kind of going to show next after I do the tangent. So I'm going to change my pen color here. I think I'm going too red, but that's okay. The tan x stays the same. And then all you have to think about is the fact that you need to take the derivative of tan. And we know generally that the derivative of tan, I mean we already know this, is secant squared. So there's our derivative. And of course you can spend a lot of time really thinking about this as composition of functions. That is by definition why it works and what it is. But decide, how much time you want to spend on, something like that, because really just using that rule from the first page is enough. So in general, if you have anything to that power of n, so this is what I've mentioned multiple times here, then the derivative is simply bringing down the n, keeping that inner piece the same, subtracting n minus 1. So this is often thought of as the generalized power rule because it does work for any of the functions of this type. And then of course you still have to multiply by the derivative of your u. So there's a lot of multiplication symbols there that you wouldn't necessarily need, but I'm just trying to spread it out and show it. Okay, so the next one here is a lot. But the chain rule is needed because you have something to the fourth power and you have something to the fifth power. So as we know, you really, really, really do not want in any way to multiply all of this out. It's not saying I haven't seen it, because I have definitely seen people try that. But there really is no point at this stage. You just want to use your chain rule and then maybe do some simplification. Okay, so we are going to use the product rule here. We do need the product rule. And we also need the chain rule. So now we're getting into this idea of using multiple rules in each problem. So I'm going to write my derivative notation. Don't forget about that, f prime of x. I'm going to take the derivative of the first piece, 4, and then I'm keeping the inside the same. And again, never worry about pausing and trying something out yourself. It's a really smart idea. And then I'm going to multiply that by, I still need the derivative of the inner piece, so 3x squared plus 2. Okay. Now remember, the product rule says the derivative of the first piece, that's that whole derivative of the first piece, times the second piece, x squared plus 2 to the fifth. So that does not change at all. Then product rule has an addition sign between it. Now I'm going to keep now I can do it either way. I'll take the derivative of the second piece, 5, and then to the power of 4, keeping that inside the same. I need to then multiply that by the derivative of the inside. So again, this is the derivative of the second piece, all the derivative of the second piece. Then I multiply that times the first. So common mistake for students, of course, is just to take kind of a bit of time to get used to the idea of a couple rules at the same time. So, you'll have practice in your homework and you'll get it. So here is the derivative on the line above, but we can definitely do some simplification. So now would be the time to kind of look for common factors. So at this point, I'm looking at this piece, like this whole thing is one piece, and then I'm over here, this whole piece is my second piece. Okay, so there's a lot happening there. But I'm going to take out any common factors. So take a moment and see about any common factors. So the first question I would ask would be, what is the common factor constant? And if you're paying attention, you'll notice that it is a 2, because I can take a 2 from the 4, and I can take a 2 from here. Okay. Then I can also take out x cubed plus 2x minus 1, and notice that we have 3 of them in the first term and 4 in the second. You can only factor out the smallest number possible. And we also have that common factor of x squared plus 2. In one of the terms I have it to the 5th, one of the terms I have it to the 4th, so I can take it out to the 4th. And then what has to hang out is everything else that I did not deal with. So there's a lot happening there. For example, let me think about what I've got here. So I'm going to have, I took out, let me just double check what I have here. Okay, everything looks good. So I have a 2 left from my first term here. I've got an x cubed plus 2x minus 1, because I still, no, actually I don't have that right, because I took out 3. Oh, that's going to be my other term. All right, take that out. Nope, nope, nope. Nope, 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 nope. Nope, 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 nope. Okay. So, back to the ink. All right, so I took out the 2. I don't need that. I need the 3x squared plus 2. And then I do need 1x squared plus 2. So x squared plus 2. Okay. From the second big term here, this big second piece, I have the 5 and an x, and then I took something out to the 4th, so I'm going to have x cubed plus 2x minus 1. And there's that. That is what is left. So a lot happening there. I will do, well, I guess I'll do another term here. Let's see. So this is going to be 2x cubed, 2x minus 1 cubed, x squared plus 2 to the fourth. And then basically you could multiply out that second piece, multiply, 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 combine like terms. I mean, you know, multiply it all out, combine everything. I'm just going to give you the final line here, which would be 11x to the fourth. You'd have 26x squared minus 5x plus 8. So if you combined everything, you'd get that. And this is the most simplified version. And if anyone's like, why did we do that? I did that in this problem just because when we do some graphing of functions, there will be a point in time where it is important for us to, I mean, basically see this simplified version because we might need to do something with it. So I wanted to show what a version would look like simplified. So that's why you see that. Okay, so what I would want you to do now is to try and pause the video and see if you could take the derivative of any of these problems just to see how it goes and what you get, just to practice. So take a moment and see if you can do them, and then unpause it and see if you are right. So I'm going to do A. So this is going to be the secant. So derivative of tan is secant squared. So it's just going to look like that. And then I multiply that by the derivative of the inside. So inside stays the same. And then I do have to multiply by the derivative of the inside. So 3x squared plus 6x. Now I do want parentheses around that because it is essentially a distributive property that I don't need to write, but I do need to understand that there is a distributive property aspect to it, that it's 3x plus 6 all multiplied by the secant squared. So I did that. For the second one, the first thing I would want to do would be to write the sine of x squared plus 3 and then put that to an exponent. So I can use that generalized power rule. And what I want you to see is that when we talked about compositions, I mean, this is basically the derivative of, this is a function inside a function inside a function. And so we would actually need to use the derivative a couple times, and like the chain rule a couple times, I should say. So the first thing I'm going to do is think about my outer function, which is that raising to the power of 1/2. So the 1/2 comes down. I have to the negative 1/2. So that's the generalized power rule. The inside stays the same. Excuse my handwriting. Okay. Inside stays the same. Then I would need to multiply by the derivative of the inside. The derivative of sine of something, this is what you want to remember. Derivative of sine of something is cosine of the something. But if that something is not just x, then you need the derivative multiplying by the derivative of the something as well. So the derivative of x squared plus 3 is, there we go. So that's why it's a multiple chain rule, because it wasn't just that power rule times the derivative of the inside. The derivative of the inside required the power rule too, so we had to take the derivative of the inside of that. And then I'll just simplify this one kind of quickly. The 1/2 would simplify with the 2, and I'd have x cosine x squared plus 3 all over the square root of sine of x squared plus 3. And you just want to think about, I mean, if the problem says do not simplify, don't even do this, just leave it as the line above, that's fine. Sometimes we are just testing that a derivative can be taken. All right, and now we've got another equation of the line, so we never stop doing those. It's just a reminder that whether you need the chain rule or the product rule or the quotient rule or any of the rules, you do them the same way for the equation of the line that's tangent to a function. So slope and point Two things we need. So I'll think about the point first. We have x equals 1, and then basically we're just doing sine of 1 squared. So don't get confused. This is asking you sine of 1, which is actually asking you to find sine of some radian. This is not a nice, great number. But if you plug in the 1, you get 0, I'm going to do it to 3 decimal places, 0.708. 0.708. Okay, so that's our point. And that's, again, just put that into your calculator and you'll see that that's what you get. As far as the slope goes, we're going to need the derivative. Like I said earlier, don't forget, this is sine x squared. So when you take a derivative, you're doing 2, and then you still have your sine x, now to the power of 1 times the derivative of sine x, which, as we learned in section 2.4, and I just did earlier, is cosine x. And now, all you have to do is just plug in that 1 to see what you get. So you'd plug it in right here, you plug it in right here, make sure you are in radians, and make sure that when you do that, you get the 0.909. So now we have everything we need. So I'm going to come over here and I'm going to write the equation of my line. Y minus, and then my y value. I'm going to have my slope, and then x minus, and then I have my x value. So in this case, we just have some decimals, and so just pay attention if you're asked to do something like this. You might be told to do a certain number of decimals, so pay attention to whatever that is. We're going to add so that we can write this in slope-intercept form. That's really how we do all of these. And so we're going to add 0.708, so that should still give us something negative, and I have 0.201. Okay. So that is that problem, and that is the chain rule. So we'll be using the chain rule consistently. It just keeps coming back up, so it's not like this is it. This is just the intro to the chain rule and the understanding of the chain rule. But we use it so often, and it continues to get used in every part of our calculus series and things like that. So that is the chain rule.